All right, so this is lecture 6, and as promised, this will be the first lecture where we formally introduce the idea of feedback control. So we'll actually fully officially get into feedback control today. We spent the first 5 lectures doing really a full-blown review on the plant dynamics and studying the plant behavior, learning how to model the plant dynamics, looking at specifications and analyzing stability. And now I think it's time to close the loop and start doing some actual feedback control. When I say close the loop, I've been saying that a lot through the past lectures. I just mean that we are going to wrap this feedback loop around that plant that we had been studying in so much detail for the past few lectures, and we're going to create an overall closed loop control system. And the particular diagram that I've shown you here, this is called the unity feedback control diagram. It's called unity feedback because there's nothing in the feedback path. The feedback path just goes straight back to the summing junction here, and then we produce our error signal and the loop propagates. This is not the only type of feedback control system, but it's generally the first category of feedback structures that we analyze when you're learning control systems for the first time. Okay, so throughout this lecture we are going to discuss sort of the ins and outs of this feedback control structure, and we're going to discuss some high-level control objectives. Okay, remember the whole point of this class is to decide what goes in that control transfer function block so that the overall closed loop system behaves favorably. So if we're going to do that, we need to define what makes a closed loop system good. And so in order to do that, we're going to look at some control objectives, to sort of make concrete what makes a control system good or not. And then after that, we'll look at a little bit of a review on block diagram algebra, because I know some of you are perhaps a little bit rusty in that area. So the reason we're going to look at block diagram algebra is so that we can study the inner workings of this block diagram here, the unity feedback control system. For example, the closed loop system has to do with the transfer function from R to Y. That's the overall, closed loop transfer function. That's how the system will behave. But there are often cases when you'll want to see, for example, how the reference affects the error signal, or how the disturbance affects the control effort. So there's a lot of input-output relationships that we can analyze, but we can't really do that until we remember how to do our block diagram algebra. Once we do that, we'll look at a couple of examples of how to apply the concepts that we learned pertaining to feedback control systems, and that'll give us a pretty good basis for moving into the next steps where we actually start designing controllers and looking at the closed loop output. All right, so without further ado, let's jump into feedback control. This is a block diagram that I had drawn. That's probably the first thing that I drew in lecture number 1. Okay, so this is where we're ultimately going to go in this class, is sort of live in this closed loop structure. But it would make sense to review what all of the signals within this block diagram represent. Okay, so just very quickly, recall that when you're dealing with just a plant, like we've been doing this whole time, you've got some input U and some output Y. The input U, that's whatever input you're going to use to excite the system. So if you're going to smack the system with the hammer, the input would be like an impulse. Or if you're going to put a constant force on that system, then the U input might be a step. Okay, so U could be any type of input that you want. The point I'm trying to make here is that, well, U is actually the output of the controller in the feedback loop. So as soon as you close the feedback loop and you're applying closed loop control, you don't actually get to choose what input gets applied to the plant anymore. All you get to do is specify what's called the reference. Okay, so the reference is, well, it's the reference. It's what you want the output to be, right? So if I want to track a specific set point speed on my cruise control system, I would be setting the reference to, say, 60 miles per hour, and then you're letting the control system do the rest. And what you would like is for the output, right, the measurement output, that's what's really happening physically in the real world. You want Y to basically match the reference. Okay, so my cruise control, I say I want to be going 65 miles an hour. It's the control system's job to try and keep the measured output at 65 miles per hour or as close to it as possible. Okay, so we have the reference and we've got the measured output. The reference is basically what you want, and the measured output, that's what you actually have in real life. Some signals that we haven't talked about in the past are these two. So you've got the disturbance, which is an external input. You see there's an arrow coming in from nowhere, basically. So the disturbance is this signal is a way to capture the inevitable inconsistencies that will be experienced by the closed loop system. And I'm going to keep referring back to the cruise control example, but suppose you're cruising along the highway, you've got your cruise control going for at 65 and you're actually going 65 and everything's great. And then all of a sudden you hit either a strong headwind or maybe you start going up an incline and now you're fighting gravity. Invariably your velocity will start to drop. And so Y, your measured output, will start to dip below where it's supposed to be, right? And your reference is going to say, wait, I'm not where I'm supposed to be, so I'm going to have some non-zero error. I'd better do something, apply some control command to counteract that disturbance. But the thing about a disturbance is it's unmodeled. We never know when it's going to happen in the real world. So we just sort of say, well, here's a generic arrow that represents a disturbance in our system. I almost said in the force. It represents a generic disturbance in our system that we have to be able to account for as it comes up. Okay, so that's what a disturbance is. There's this other input entering our closed loop system. It's called V, and that's referred to as sensor noise. Sensor noise is somewhat like a disturbance in that it's some signal that serves to basically mess up our closed loop tracking ability. But the sensor noise comes from a different source, right? The sensor noise is not from a strong headwind or an incline on the road. The sensor noise actually has to do with, well, how do we actually capture the measured output so that our algorithm can process it numerically? What I mean by that is if you have your cruise control set to 65 miles an hour and you're actually going 65 miles an hour, that's all good and well. But how do we know that we're actually going 65 miles an hour, right? Any physical real world signal like Y, whether it's speed or temperature or angular displacement, whatever it happens to be, we use some type of physical sensor to measure that so that we can basically turn that physical property or physical parameter into a numerical value so that we can compute it, right? And so in an automobile, for example, the cruise control, there's some sensor that's measuring the speed of the wheel and calculating how fast you're actually going. In a HVAC system, for example, there's a thermostat on the wall with a thermometer that's constantly measuring the current temperature in the space and converting that into a number. And the point I'm trying to make here is that basically there is no such thing as a perfect sensor. There's always some type of error associated with measuring the actual physical property, Y. And so you're going to get a little bit of a discrepancy between what the true variable is and what you're actually seeing in your feedback control loop. And that discrepancy is just modeled as another external disturbance, which we just call V, the sensor noise. Okay. The rest of the other two signals, U, we'll start with E actually. E is a really important signal in the feedback structure because the error signal is the input to our controller, C, right? And the error signal is so important because it contains information about both what we want and what we actually have. Okay, so the error, if you just look at the block diagram, is basically R minus this signal, which is if V is 0, if there's very minimal sensor noise, then E is equal to R minus Y. And r minus y is literally the difference between what we want, r, and what we have, which is y. Okay, and that's very important information to have for the controller, because now the controller can say, oh, anytime the error is non-zero, that means I should do something uh, to counteract whatever disturbance is causing that non-zero error. So if the error, for example, if I've got my cruise control set to 65 miles an hour, r is equal to 65, maybe I hit a strong, maybe I'm going up an incline now and my speed drops to 60. Okay, so now my error is r 65 minus 60. My error is actually equal to 5. Well, that non-zero error is going to be processed by the controller, right? The error is the input to the controller, and the controller, depending on how we design it, will output a control command. Okay, so the controller will say, oh, I've got an error. I'm 5 miles an hour slower than I should be going. I better apply more throttle to the engine to speed up the vehicle. That's what U represents. That's the control command, and it's the output of the controller. Okay, so that's what the control command is. Notice in the absence of a disturbance, if there is no disturbance, that control command U becomes the input to the plant. So then the cycle basically just perpetuates, right? So the output of the controller is the control command, and that control command is basically converted through some type of actuator into the actual forcing function of the plant. So the control command is what actually changes the state of the plant. It'll make it go faster or slower or accelerate or decelerate and so forth. Okay? Now this loop just propagates at however fast you want to sample. So in some cases this loop might happen 100 times a second. In other cases where the dynamics move much more quickly, you might have to run this loop at 10,000 times per second. Okay, so this loop is just always running, always monitoring the error, and the controller is always processing that error to produce some control effort. And so that's how sort of the basic overview of the feedback structure works. This is really just a review. I mean, I've mentioned a lot of this in the first lecture, but this is the starting point for today's lecture. Today's lecture is really all about, what does it mean to do control design. Right? After all, we are trying to figure out what's going inside of this controller block, remember, so that the closed loop system behaves in a favorable fashion. So control design, as concisely as I can put it, is the following. Okay, so this is basically our working definition of control design, and I understand it's very vague, right? Basically, it says the process of control design is the process of finding some transfer function C of S such that the closed loop control objectives are satisfied. So this should really be updated to say closed loop control objectives. So whatever that means, the control design process is basically find a controller such that whatever we determine to be a good output is satisfied. Okay, so it's very vague, it's high level, but we have to start somewhere. All right. Okay, so it's probably a good idea to talk about, just jump straight away into what are those control objectives. What makes a closed loop system good versus not good? Okay, and this is up for debate. I mean, different controls engineers are going to have different definitions for what's good and what's not good, and where do we place our emphasis in our control design. And so what I'm going to do is I'm going to outline 4 control objectives. And these are very general. And so wherever you end up working, if you end up in this field, your control objectives are going to consist of one or more of these general control objectives. Is pretty much a guarantee because these are so fundamental to control design. Okay. In fact, you could probably guess what the very first and most important control objective is. I'll give you a second to think about it. And your hint is, well, look at lecture 5. Okay, so if you said stability is the number one most important control objective, you would be right, in my opinion. Okay, you cannot talk about any subsequent control objectives like speed of response or robustness or tracking capabilities if your overall system is not stable, right? Stability is sort of a baseline objective that has to be satisfied in order to talk about any other um, kind of control objective. Okay, so stability is your number one most important control objective. However, remember that in the open loop sense, what we talked about last lecture was basically this. A system is considered stable, like the plant is considered stable if you apply an impulsive input, like like a delta impulse function, and your output converges to zero. Right? That was a fundamental definition of stability. So you have some dynamic system, you ping it with a hammer. Does the output eventually converge to zero? If yes, that system is stable. However, when you look at our closed loop system, right? If you look at this block diagram, I'll give you a minute to think about it, but how many inputs and how many outputs are there? That's the question now. Okay, so if you look at this block diagram, there are actually three external inputs. You've got your reference, but you also have this disturbance, right? That's an input to our system that's unmodeled. We don't know what it is until it occurs. And we also have sensor noise. So there's three inputs. And we also generally consider this block diagram to have three outputs. Now understand that Y is the only output that sort of goes externally, right? That's the only one that ultimately matters at the end of the day. However, we often consider the output of the controller as an output, and because the error signal is so important, we often consider that as an output as well. So what I'm saying is, in the open loop sense, yeah, the idea of stability is for the one input and the one output, this relationship has to be true. But for the closed loop sense, closed loop stability really means that for the three inputs and the three outputs, that same property has to be true. So for any one of these, if you apply an impulsive input to R, V, or W, the system in the closed loop sense is not considered stable unless all of these potential outputs converge to zero, right? So what I'm saying is there's basically 9 combinations of input outputs here that you have to be aware of in order to consider the closed loop system stable. Okay, so that's the definition of stability, and that's the most important control objective, is to generate a control system that is stable across all input-output relationships. Okay? The second one, I mentioned that there's 4 of these. The second one is called tracking. Okay, so assuming you have a stable system, the next most important control objective is called tracking. And the idea of tracking is that y of t follows r of t. Right? So under ideal circumstances, basically refers to when W and V are equal to 0. So assuming that there's no disturbances and we have a perfect sensor, the tracking control objective means that y of t basically mimics r, right? So in other words, right, if you, right, essentially the cruise control example is you're setting a certain set point velocity. Maybe this is 65 miles an hour. Well, you want your output, right? It may not follow that exactly. It may do something like this, but ultimately you want the output to track the reference. Okay, so essentially tracking means that you want the error, the steady state error, to be 0. So as t approaches infinity, you just want the error to be 0. That's what the tracking objective is. Okay, so the next one is it's related to tracking, but it's a little bit different. It's called regulation. And regulation is sometimes referred to as disturbance rejection. And regulation is the idea that it assumes that you're already tracking. So it's the idea of maintaining the tracking state. So ideally you'd like to keep y of t as close to r as possible um, in the presence of a non-zero disturbance. Okay, so that's the idea here, is that regulation is the ability to maintain the tracking state even if there's an external force trying to push you off track. Okay, so it's related to tracking, but it's different in the sort of underlying assumption. Regulation is this idea of, okay, again, back to cruise control. If you're cruising along going 65 miles an hour, you're tracking, everything's fine. How well is your control system able to overcome, say, a strong headwind or an incline and maintain that tracked state in response to that non-zero disturbance? So that's actually a different objective, and it requires a different control strategy to maintain that tracking state. Okay, so tracking and regulation are related, but they're different. There's subtle differences there. And then the last one is called control effort. Sometimes this is referred to as the cost. Okay, so basically to satisfy control objectives 1 through 3, you need some type of control algorithm, and you need some type of actuation and some type of sensing um, in order to close the loop and run the closed loop system. Now, if you design a controller that, for lack of a better word, overreacts to very small errors, so like if you have just a tiny little error, say you want to be going 65 miles an hour, but you're actually going 64, and so you have a small error. If your controller gives it a ton of throttle to try and compensate for that, that's referred to as like an expensive controller. It's a higher authority controller, and that costs more on many fronts. So, I mean, financially, it costs more because you'll end up having to probably use higher quality actuation and sensing to achieve that control effort. You'll need, higher quality computing to sample at a faster rate. But the cost associated with it is also in terms of control efforts. Okay, so basically, if the error is small and the corresponding U signal is large, that's referred to as like an expensive controller. So it's a higher authority controller, and the idea is you would like to. The whole goal of this control objective is to keep U of t small. This is basically, you'd like to keep the control effort as small as possible while still satisfying the other control objectives. Okay, so basically what I'm trying to say, here's an example of that. So let's suppose you're starting. So this is like a cruise control example again, but it's a little bit different. It's like you're assume that you're at a standing start, right? So you're at rest, and then you're trying to track this step reference of say 60 miles per hour. Okay, so theoretically speaking, you know, ignoring all the effects of like wheel slippage and physical capability of the system, theoretically you could design a controller to take a vehicle from 0 to 60 and track perfectly, and the response could look something like that. Okay, that's theoretically possible, and maybe this is a timestamp of 0 and this is a timestamp of 1. Right, so 0 to 60 in a fraction of a second. Okay, so I know it's not practically possible, or maybe it is, but it's practically unfeasible, but theoretically this is possible. And the point that I'm trying to make is, even though this is theoretically possible, the control effort, okay, so we're now looking at U of t, the control effort required to implement this response may look something like this. Right? So it might look something like this, and the effort may be proportional to, say, the horsepower of the engine. So it may require a certain horsepower to implement a given control effort, and to achieve this response, this orange response, which is the output over here, you may require a control effort that looks like this. In other words, even though theoretically it's possible to design a control system that takes a vehicle from 0 to 60 in under 1 second, the theoretical basis for that would be to provide upwards of 3,000 horsepower for that initial acceleration. Okay, so the point is theoretically things are possible, but in reality, you kind of need to do a reality check. It may not be feasible to implement that controller because, well, at least I don't have a vehicle capable of putting that much power to the ground without slipping or breaking something. Okay, so the idea of control effort is basically just a balancing control objective. It's sort of a sanity check on the other three objectives. Right, so it's easy to get carried away with control design and say, "Wow, this is a fantastic controller." If you look at this control objective with the control effort, you might find that, oh, well, if I wanted to implement this controller, it would be impossible to do. Okay, so this is the fourth control objective, and what we're going to find later is basically this control objective, the fourth control objective, kind of fights against the other three. So it basically becomes this balancing act of, well, how do you determine what's the best for your application? Okay, so this is like the overview of the four control objectives that I want to outline in this lecture. These are very high level, and then as you get more capable of doing control design, you'll find that there are subtleties to these, and there's more advanced control methods for, say, achieving regulation or stability or tracking. Okay, but this is sort of a high level first pass at your control objectives. We're going to revisit those control objectives in a little bit, but what I want to do now is to take a little bit of a detour and review some block diagram algebra, because what I want to do later is revisit those control objectives as it pertains to the particular unity feedback block diagram that we have been studying for this semester. Okay, so if we look again at our unity feedback control structure, we've got our basic block diagram, and we notice that there are several inputs and outputs. Okay, what we need to do is start getting our hands dirty, so to speak, with our actual unity feedback control structure. Like, we want to be able to analyze the effect of any one of the three inputs to any one of the three outputs. And in order to do that, we need to be able to compute transfer functions sort of at will between any pair of inputs and outputs. Okay, so to do that, we really have to refer back to our block diagram algebra, which is just a way of block diagram algebra will allow us to simplify this block diagram to a point where it's apparent what the input-output relationship would be for a given input-output set of variables. Okay, so the closed loop transfer function, okay, when we write closed loop transfer function, that's the overall transfer function that governs this input-output relationship. And what we're talking about here is a transfer function from the primary reference input to the primary measured output. Right? This is the so-called main closed loop transfer function. Okay, and this you may have seen in a previous lecture or in one of the assignments has the form of CP over 1 plus CP. Okay, so this may look familiar because this is a pretty common transfer function. And the question is, how do we know? Where did this CP over 1 plus CP come from? Okay, in order to derive that, we use something called block diagram algebra to basically reduce, this should be R, to basically reduce, to solve for the ratio in question. So we want the relationship transfer function from R to Y, so we would need to solve for it in terms of C and P. There are a couple of different ways that different textbooks or instructors will go about explaining block diagram algebra. The way that I find that's most transparent and easily understood is basically starting from scratch and just basically taking a lap around the block diagram and extracting all the information you can. On the other hand, there are a set of rules that you can memorize to try and do block diagram reduction. The reason I don't teach those is because you can derive those easily if you know the fundamental relationships and motivations for how those rules come out. So I don't expect you to memorize any block diagram reduction rules or anything like that. What I will do is I will basically show you from start to finish how to compute a transfer function given this block diagram. Okay, so without further ado, this is your quick review on block diagram algebra. If I want to find a transfer function from R to Y, okay, this is what I'm trying to compute. The first thing you have to do is identify the inputs and outputs. Okay, so for this block diagram, we have one input, two inputs, and three inputs. These are all external inputs, meaning that they're just signals that come in from outside, right? It's not like a signal that's being fed back or some type of internal signal. These signals all just start from outside of the block diagram. The input, right? The input is always the denominator of the transfer function, right? So we always say this is always read as the transfer function from R, right, to Y. It's the thing in the denominator to the thing in the numerator. So for this relationship, from the transfer function from R to Y, we are only concerned with the input R. And this is a key point here, is that for the moment, I don't care how W or V affects Y. I only want to know how R affects Y. And because I only care about how R affects Y, I can let the other inputs equal 0. Okay, so that's the first step, is identify the input that you're concerned with and let the other ones equal 0. After you do that, you can actually redraw the block diagram. Okay, so after you let the appropriate inputs go to 0, you'll redraw the block diagram without those inputs. So in this case, there's no W and there's no V. So this will just be fed all the way back here. And this will simplify things a little bit. Okay, so there's no more V, no more W. And now this is our reduced block diagram. And then the next step that you're going to do is to sort of, take a lap all the way around the block diagram. Don't miss anything. Just go all the way around and basically try and extract equations from the block diagram. Generally, the two places you're going to extract an equation is from a transfer function block or a summing junction. Those are really the only two places you're going to get any meaningful equations. Now, the transfer function block, so anytime you see a block, you can get an equation out of that. And just remember that the transfer function, right, P, right, that's equal to the Laplace of the output over the Laplace of the input, right? It's equal to the ratio of output over input. So by extension, the equation that we can gather from the P block would be, if we're writing it in a single equation, would be y is equal to P times U. Okay, you see how it works? So according to this block diagram, the plant has an output of y and an input of u, and the transfer function relationship is that P is equal to y over u. So if we just multiply both sides by u, we get that y is equal to P times u. Okay, so that's the equation that we can get. Now realize that this is a bit of an abuse of notation, because I'm intermixing time domain signals like little y and little u with S domain functions like s. That's okay for now, only because we're just trying to extract the input-output relationships within the block diagram. We're not actually saying that little y of t is equal to big P of s times little u of t. That's not actually true, but this is a relationship between all three of these variables. That's all we're really concerned with. Okay, so here's one equation. The second one comes from the controller block. The controller block appears to have an output of u and an input of e. So C is equal to u over e. Or another way to write that is U is equal to C times E. Okay, so again, we're just going around this, taking a lap around the around the block diagram and extracting as much information as possible. Like I said, if you see a summing junction, that's another place where you can extract a piece of information. And the summing junction would say that the output of the summing junction is equal to the sum of all of its inputs. So E, which is the error, that's the output. And there's two inputs here. So it's going to be E is equal to R plus negative, that's why there's a negative sign here, negative this signal, which is Y, right? It's picked off all the way from over here. So E is equal to R minus Y. Now, just sort of pausing for a second, we have extracted all the information we can from this block diagram. There's no other place to get any more information. Once you've done this step and you've got this set of equations, you basically now just need to go back and eliminate all the variables that are not either R or Y. Okay? What I mean by that is if you just start with this equation, for example, Y is equal to P times U. I don't want U in my final ratio because U is not a variable of interest. So I'll find an equation, hopefully, that I can use to plug in for that. Right? So Y is equal to P times U, but U is equal to C times E. Okay, so I've eliminated the U variable. Unfortunately, I've done so by introducing the error variable. But that's okay because I have another equation that contains another equation for E in terms of other variables. Okay, so Y is equal to Cp times E, except that E can also be expressed as R minus Y. Okay, now at this point, you should be able to identify that you're basically finished because I only have the input-output variables that I am concerned with. I have Y, R, and another Y over here, and then of course there's C and P are going to be part of this equation. But the important part is that I've eliminated U and E. And in this case, it's a simple matter of now solving for the ratio of Y over R. Okay, so now I've got Cp times R minus Cp times Y. If I distribute the Cp through into the right side of the equation, if I move Cpy to the other side, I get 1 plus Cp, and I could factor out my Y, and I'm left with Cp times R. Okay, all I'm going to do now is solve for the ratio of Y over R, and I can do that by dividing both sides of the equation by 1 plus Cp. And so that's where the Cp over 1 plus Cp comes from. And remember that this is technically little y of t over little y of r, right? But earlier on I was kind of abusing this notation, so I know that this is the relationship between r and y. Now I can just go ahead and say, well, this ratio is equivalent to the transfer function from r to y, right? So I just make that substitution there. Okay, so that's how you compute your closed loop transfer function. You can do this for any of the essentially 9 input-output relationships associated with this unity feedback block diagram structure. Just for good measure, let's do one more example to make sure we understand this. Let's figure out what the transfer function is from, say, transfer function from W to E. Maybe we want to know how the disturbance is going to influence the error signal, little e of t. Right? So we want to solve for this transfer function, which means, right, because W is the input of interest here, I don't care about R or V for this problem. Okay, so I can eliminate those, and I can redraw. So let's let R equal V equals 0, and with that assumption, I can redraw the block diagram as really it's just going to look like this. So there's C, I still keep W, but I'm going to get rid of V and R. Okay, so this is the entire block diagram. There's no R here and there's no V here. This is still labeled E, this is still labeled U, and this is still Y. Okay. Remember what we did last time. So after we simplified the block diagram, after we redrew it, then we took a lap around the block diagram and extracted all the equations that we could. Okay, so that's the step we're at here. We've redrawn the block diagram. And now we're going to take a lap around this block diagram to try and get all the information that we can. Okay, so it doesn't matter where you start, you can start anywhere. Let's just start at the first summing junction here. So E, right, the output of this summing junction should be equal to the sum of its inputs. Well, there's only one input in this case. So the equation here becomes E equals negative Y. Okay, so that's one equation. Moving on to the controller, just like before, U, the output of the controller, equals the controller times its input. The next one here, so in this case we actually have two summing junctions. So the output of this summing junction should be the sum of U plus W. The only thing is this signal doesn't have a name. Like, we don't know what that signal actually is. And if that's the case, you can just give it a name, right? We'll just label this signal. We'll call it Z, for example. And now Z is equal to U plus W according to this summing junction. Now, keeping that same variable Z as the input to the plant, our last equation comes from Y is equal to P times its input, which is Z. Okay, so I don't think that there are any other equations we can extract from this. We've extracted 4 in this case. And what we want to do now is the rest of it is just eliminating the variables that we don't care about. So we only want the variables W and E, and of course C and P to appear in our equation. So we want to eliminate Y, we want to eliminate U, we want to eliminate Z. And yeah, so those are the ones that we want to eliminate. If you're ever curious as to which one you should start with, generally, like what I do is I identify the output that I'm interested in, and I start with an equation that contains that output by itself. It's just, you don't have to do it that way, but it seems to work out that way. Okay, so starting here, E equals minus Y, but I don't want Y in my equation. But I have an expression for Y. It's P times Z if I use this equation over here. But I don't want Z in my equation either. So I can replace Z with its equivalence, which is U plus W. So that's pretty good. I've eliminated Z, I've eliminated Y, and now I've got E and U and W. So the only thing I have to do is eliminate the U so that I'm only in terms of E and W. And if I've done this correctly, I should have an equation that only contains U. Okay, so minus P times, I'll replace U with C times E. And now if you look at this equation, which is basically from here to here, that equation only contains E and W, which are the input and output that we care about, and then C and P. Okay, so at this point, it's a matter of algebraically solving. So I've got E is equal to minus CPE minus PW. So all I've done is distributed this negative P into the parentheses. Okay, so then I'll move this minus CPE to the other side, and I get 1 plus CP. E is equal to negative PW, and the rest here is pretty much trivial. I'm just solving for the ratio from W to E as minus P over 1 plus CP. Now again, this relationship is the same as that from the transfer function from W to E in the Laplace domain, which is the original problem that I set out to solve for, transfer function from W to E. Turns out that is minus P over 1 plus CP. Okay, so this is a very brief review of block diagram algebra, but there's really not a whole lot more to it. There's nothing special that I have to memorize. I don't have to memorize rules about blocks in parallel or series or in feedback. If I remember these fundamental rules about how to reduce a block diagram and solve for the proper ratio. Okay, so remember that I mentioned that there were 3 inputs and 3 outputs to this primary feedback control block, right? You've got R, W, and V as your inputs, E, U, and Y as your outputs. I think it would be a poor use of time for this lecture to derive the remaining 7 transfer functions. So what I'm going to do is basically, I'll just tabulate them for you, okay? So this is a matrix of transfer function numerators. And we're only going to tabulate the numerators because notice that the denominator for both of the transfer functions that we derived were the same, 1 plus CP. It turns out for all of the 9 closed-loop transfer function relationships, the denominator is always 1 plus CP, which, by the way, is another reason it's called the characteristic function, because it doesn't change. It doesn't change as you are interested in the different input-output relationships in the closed-loop transfer function. Okay, so 1 plus CP is always going to be the denominator. So this matrix is just going to tabulate the numerators. And it looks like this. Some of these we've already done. So the inputs are R, W, and V. Outputs are Y, E, and U. And the transfer function numerator from R to Y, we've already computed that one. It's CP. The transfer function numerator from W to E is minus P. That's the one we just computed. And then so this is going to be the rest of them. Okay, so this is like a matrix of the transfer function numerators. Now the key here is that denominator is always the same. It's always 1 plus CP. Okay, so if the way to read this matrix is if I want to know, say, the transfer function from V to U. Okay, so if I want to know that transfer function, it's as easy as referring to this table, grab the numerator, which is minus C, over 1 plus CP. Okay, and so there's no block diagram algebra you'd have to do to derive that. Okay, so that's how you would read this table. Now, there's always a catch when you try and simplify things, right? So this table, it only applies for unity feedback. Right? It only applies for the one block diagram that we've been talking about so far. Okay, so really it only applies for this picture up here, right? So the matrix only applies for the unity feedback structure. In some cases, you may find that the controllers move to the feedback path. Or in other cases, you may find that there's additional filters pre or post block diagram, in which case the matrix here no longer applies. Right? So this is just a shortcut for unity feedback control systems. If the block diagram changes, you have to actually go through the block diagram algebra yourself to figure out what those transfer functions are. Okay, but for our purposes, I think it's good enough to say here are the 9 transfer functions associated with our unity feedback structure. And now, as promised, what I want to do is to revisit I want to revisit those 4 control objectives from earlier and try and draw some additional conclusions from that. Okay, so all we're going to do now is, again, revisit our control objectives. The first one, of course, was stability. Well, how do we guarantee that the closed loop transfer function is going to be stable? Well, this is just a rehash of the lecture 5 material, right? If we want to guarantee closed loop stability, all it means is that we want the real part of all of the closed loop poles, right? The real part of all the closed loop poles to be negative, right? So in other words, we want all the poles to be in the left half plane, and if they are, then we're stable. So that's how you guarantee closed loop stability. So that doesn't really have to do with the transfer functions that we just derived. For tracking, the second one, this one's a little bit interesting. Okay, so for tracking, what we want to do is basically say that for any reference that we're trying to track, right? For any value of R, whatever R happens to look like, if we want the system to track, we basically want the error to be 0, right? Right? For whatever R happens to be, we want Y to follow that R, and therefore the error should be 0. Okay, so the goal essentially for tracking in terms of transfer functions is that we want the relationship, we want the transfer function from R to E to be small. right? We want that transfer function to be small. What that would say is for any given denominator, the numerator is always 0. That's great for tracking, okay? The transfer function from R to E, we actually know. If we consult our table, the transfer function from R to E has a numerator of 1 and a denominator of 1 plus CP. So we can replace the transfer function from R to E with 1 over 1 plus CP. So if we want to be able to achieve the tracking control objective, what we want is for the relationship 1 over 1 plus CP to be small. Okay? Small just means, small refers to the authority of that transfer function. It doesn't necessarily mean that this is a numerical value and that number is small. It just means that this transfer function has low authority, which means regardless of whatever input you have, the output is always pretty small, right? So in other words, regardless of whatever R is, the error is going to be pretty small. Okay, so looking at this ratio as a simple fraction, if we want to minimize this ratio, what it means is that we want C, right? C is the only thing we can change in this equation. We want C to be large. We want C to be large, right? So if we're talking in pure, scalar constants, like just pure numbers, if C is a large number, then this ratio is a small number, and that's what we want. Since we're talking about transfer functions, we want C to basically be high authority. So a large value of C, quote unquote, means that it's a higher authority controller. And higher authority just means that for any given input, the output is pretty large, right? So this is what I was talking about earlier. It's a very sensitive controller in that even for small errors, it produces a large control effort. Okay, so for tracking, generally speaking, we want a high authority controller. The third objective was regulation. Right? And for regulation, what we want is, remember, for regulation, we're assuming that we're already tracking, and we just want to keep it that way in the presence of a non-zero disturbance. Okay, so what we want is for the relationship between W to E to be small. In other words, no matter what disturbance we're faced with, the numerator, or the error in this case, should stay close to 0 as possible. Right? So we want this relationship to be 0, and according to our matrix, the transfer function from W to E is minus P over 1 plus CP. Okay? So for regulation, we're trying to minimize this ratio of minus P over 1 plus CP, and just like before with tracking, this would imply that we want a large C. Right? So again, we want a high authority controller to achieve the regulation control objective. These two, control objectives, tracking and regulation, it kind of makes sense intuitively that you'd have a more sensitive, higher authority controller to achieve those. This is just sort of the theoretical proof of that. Now here's the kicker. The fourth control objective was control effort, right? Essentially the cost associated with achieving these other control objectives. So the control effort, for the control effort, what we want is for the relationship from R to U to be small. What this means is that regardless of what reference we're trying to track, I want to maintain a small control command U. Okay? So it's this relationship that we want to minimize, and the transfer function from R to U is C over 1 plus CP, according to our matrix. So this is the ratio that we want to minimize. Now, if you look at the difference between this and for tracking and regulation, you see that there's a C in the numerator. Okay, so the way to minimize this fraction actually is to have a small controller. Okay, we have the case where we want C to be small. And if C is small, then we minimize this ratio, okay? Because C itself is part of the numerator. So if C approaches 0, then this ratio approaches 0 as well. So what we're saying is to achieve the control effort objective, we want a low authority controller, which makes sense because it's C is dictating the output, which is the control command U, right? The output of the controller is U of T. So if we want to minimize U of T, regardless of whatever R is, we want to have a lower authority controller. Okay, so this is still pretty high level and pretty theoretical, but it really highlights this conflict of control objectives. Okay, so what I'm saying is that these are conflicting control objectives. Basically, you can't have all of them with a single controller. You kind of have to pick what's more important for your particular application. Okay? If you have all the money and resources in the world, you can do fantastic tracking and regulation, but it's going to cost you, right? You're gonna have enormous control effort, which may require higher quality components to achieve that. On the other hand, if you're using an Arduino platform, for example, to implement a control scheme, you are limited by, for example, the amount of current that you can put out, or maybe the resolution of your PWMs or the sample rate. Those all play a factor in the control effort. Okay, so you may not be able to get as high a level of tracking and regulation, but you will certainly be at a lower cost if you use a hobby grade platform like Arduino. Okay? The point is, no matter what you use, no matter what your system, these control objectives are always going to be fighting each other. And so the overall idea that I'm trying to convey to you is that control design is not about the best controller. It's about finding the right balance of satisfying these control objectives as it pertains to your application. Okay, students will always come up and say, well, so, we learned a bunch of controllers in this class. Which is the best one? There's no answer to that, right? There's no such thing as the best controller. It's all about what are the requirements, what are the design requirements for the particular job that's at hand. Okay, so these are your control objectives. This is a very it's a brief overview of feedback control, but we've covered some ground. We've covered a lot of ground in that we've picked up on block diagram algebra, and we've learned that there are these fundamental objectives that we're trying to satisfy, and furthermore that those objectives fight each other, right? You can't have all of them. Okay, so before we wrap this lecture up, I want to do an example that illustrates a number of things. First of all, it illustrates how these design objectives fight each other, right? So it's a direct example of this sort of conflict of design objectives. But it actually also takes us through some good practice in analyzing control systems and kind of looking at various system responses. Okay, so let's look at this example here. For this example, we have a simple first order plant and a simple proportional controller. Proportional controller, gain controller, constant value controller, those are all saying the same thing. Basically that the transfer function itself for the controller, C of S, is just a constant value. It's just a scalar constant. Okay, so C of S is not really, it has no poles, no zeros, it's just a gain. Okay. Now, what we're going to do is we're going to look at the closed loop step response once we close the loop on this set of plant and controller, right? So remember, we're plugging this plant and this controller into our, we're closing the loop on this plant, and we're doing so in this fashion, right? So just for context, the C and P that we've defined here go into this block diagram where they appear. Okay, so this is the closed loop transfer function. For this controller in this plant, the transfer function that we want to consider is, again, the transfer function from R to Y. That's our overall closed loop transfer function. And we know, because we already derived it, that's equal to Cp over 1 plus Cp. Okay? So in order to compute G, you actually need the controller and you need the plant. And once I have them, it's just a matter of plugging in, like so. Right? So just plugging in C and P everywhere you see it, and then of course you want to reduce this to a simple rational function. So just one polynomial in S divided by another polynomial in S. And so this is what we get for a closed loop transfer function. Before we move forward with this example, I want to reiterate something I think I mentioned in a previous lecture. Once you close the loop, so once we implement this closed loop system, the system no longer behaves according to the open loop plant dynamics. Right? So you might have a first order plant sitting on your lab bench or sitting in your garage or wherever you are. That physical system may have dynamics that look like this, maybe 1 over S plus 1. When you close the loop around that and you apply feedback control, it doesn't behave that way anymore. It behaves according to the closed loop transfer function. That's a fundamental idea behind feedback control, is that you change the behavior of the output of the system according to the closed loop transfer function. Right? That's the whole value of feedback control, is that you are able to change how that system behaves using feedback, using a feedback structure. Okay. So given this, what we want to do, at least for this example, is we're going to look at a step response. We'll take a look at how this closed loop system responds to a step input, but we're going to do it somewhat generically. We're not going to plug in any values for k. How do I compute little y of t given that little r of t is equal to 1, which is a unit step input? Well, we go back to lecture 2 when we basically formulated how to compute the forced response. Right? So if I want to know how this closed loop system is going to react when I apply a unit step input, I already know how to do that. Right? I already have the tools to do that. Right? So G is equal to the transfer function from R to Y. The forced response would say I can compute for the output in terms of G and R. Now I have G of S, that's this guy right here. I need R of S, which I can get by taking the Laplace transform of little r of t. Right? So it's going to be 1 over S. So big Y of S is equal to G times R. G is K over S plus K plus 1. And big R of S is 1 over S, right? And what I'm going to do is basically take the inverse Laplace of this so that I can compute my actual step response, which is little y of t. Okay, so I'm not going to do this portion here because that's what lecture 2 was all about. We're going to do a quick partial fraction expansion, solve for the coefficients, and get our inverse Laplace. What's important here is to know what the form of this output looks like. Okay, so assuming I could take the inverse Laplace correctly, this is what my actual analytical step response will look like. Okay, this is the part that I want to highlight. This is the part that I care about for this exercise, right? So we already know how to take the inverse Laplace of this, and that's the part that I'm skipping in this example. Okay, so if you're confused about how to take the inverse Laplace of this, refer back to lecture 2, where we talk about the Laplace transform. Okay. This is what I'm concerned with. Y of t, which is the step response of the closed loop system, has this form. Now, what this looks like as a function of time is the following. Okay, it's basically a constant value minus a decaying exponential. Okay, so let's for the time being, let's assume that t is equal to 0. At t equals 0, I have e to the 0, which is 1. So I basically got 0, right? The whole parentheses is 0, and 0 times k over k plus 1 is 0. As t approaches infinity, e to the minus infinity t, e to the minus infinity, that approaches 0. And so I'm left with just k over k plus 1. So as t approaches infinity, I'm approaching this value, right? But in the meantime, in the middle, between 0 and infinity, I'm basically just taking this constant value, k over k plus 1, and I'm subtracting off that decaying exponential. Okay, so generally speaking, the response is going to look like this. This is my actual step response, right? Okay, my closed loop step response. But remember, it's all in terms of k, which is the controller gain. Okay, the reason I kept things generic here is that we can see sort of what happens if we increase k. Right? So as we increase k, if we were to increase k, well, first of all, look what happens here. K appears in this step response in a number of different locations, right? It appears in this constant, which is k over k plus 1, but also the rate of decay of that exponential function. Okay, so if we increase k, okay, so let's just suppose that k equals 1 for this green plot. Okay, let's just assume that this is like k equals 1. If k equals 1, then the final value that we're going to achieve after all the exponential decay part dies away is going to be 1 over 1 plus 1. So 1/2, right? If k is equal to 1, remember we're trying to track a value of 1. Our step reference is 1, right? So for k is equal to 1, our reference hasn't changed. We're always trying to track a value of r equals 1. This is what we want to be tracking. So when k is equal to 1, our final value is actually just 1/2, right? It's k over k plus 1, so it's 1 over 1 plus 1. And our rate of decay is like e to the minus 2t, okay, when k is equal to 1. So that might look something like this, right? So this is k equals 1, and this is y of t for k equals 1. If we were to increase k, now this is a point I was trying to make. If we were to increase k, two things happen. First of all, the final value gets closer and closer to 1. Okay, for example, if k is equal, not 1, but equal to 10, for example, then the final value works out to be 10 over 11, or 0.909090, right? So that's way closer to the value that we're trying to track. Also, it gets to that final value more quickly because the exponential part decays faster. Okay, so if we increase k, we actually get better tracking. We get better tracking, and we get faster convergence, right? Because that exponential portion is going to decay quicker. So for k is equal to 10, for example, our response looks more like this. Right? So this would be for k is equal to 10, and that would be the step response. Right? So it's kind of looking like, well, these are pretty good responses. Why don't we just keep increasing k so we get better and better and better tracking at a faster and faster rate, right? I mean, take the extreme, for example. Take the extreme case. What if k is equal to like 1,000? If k is equal to 1,000, we will settle at a value of 1,000 over 1,001, which is, for all intents and purposes, equal to 1, almost perfect tracking. And we get there almost instantaneously because that exponential portion is going to decay super quickly. So if k is equal to 1,000, our response might look something like this, right? So this would be k is equal to 1,000. And so it appears that the higher k is, the better we're going to track and the faster we're going to converge. Sounds too good to be true, right? And that's because it is, right? This is what I mean by the design process is often limited by the reality of what can be implemented. Okay, so theoretically, we'll just keep increasing k and getting better and better performance. But let's take a look at the other side of the coin. We always need to be sure that our controller design is feasible. And one way to analyze that is to look at the transfer function from R to U to study the effect of the control command. Okay, the transfer function from R to U is, according to our matrix, C over 1 plus CP. C over 1 plus CP, when I plug in my controller, so C is equal to K over 1 plus K times my plant, which is 1 over S plus 1. This transfer function is just plain different. It's not the same as CP over 1 plus CP, right? If I simplify this transfer function to a rational function, it looks like this. The numerator is ks plus k, and the denominator is still the same, right? We've got the same characteristic equation for all of them, right? So the only difference between the transfer function from R to Y and the transfer function from R to U is actually the numerator here. Okay, so that's something good. Let's look at the same step response for this transfer function. Right, remember that R of t is we still want to see what the step response looks like. So where R of t is equal to 1. If R of t equals 1, then our big R of s equals 1 over s. And if we give this transfer function a name like h, for example, then I can compute the forced response for u. So essentially u of s is equal to h times r. Well, I've got my h, it's right here. I've got my r, it's right here. So big U of s is equal to ks plus k over s plus k plus 1 times 1 over s. Now what I want to do is, again, take the inverse Laplace of this, and when I do that, I get my little u of t. So the actual control command profile which will be applied in this feedback control loop is given by little u of t here. And when I take this inverse Laplace, I get something similar to my last example of from R to Y, but it's a little bit different. It's actually critically different in that it looks like this. Okay, so I got this by taking the inverse Laplace of this thing up here. Okay, now remember, one thing I mentioned earlier is that when you apply a feedback control system, when you implement feedback control, you no longer get to decide how the control effort is applied to the plant, right? You are not driving the plant anymore. The control system is driving the plant, right? When you implement feedback control, you just are specifying the reference. Here's what I want in the output, and you're letting the controller figure out how to apply u of t to the plant to achieve that. Okay, so that's what this is here. This is the actual control command that's going to be applied to try and track a step reference. Now, if we look at what this function looks like as a function of time, or this is going to be u of t as a function of time. Let's say when t is equal to 0, I've got 1 plus k e to the 0. E to the 0 is 1. So I've got k plus 1 times k over k plus 1 again. So at t equals 0, the initial value for u of t is actually equal to k, right? When t equals 0, u of 0 is actually equal to k itself. And k, again, is the gain in our controller. And then, as time goes on, this exponential will decay to 0, and so we'll be left with the final value of k over k plus 1, like so. In between 0 and infinity, we are simply just decaying according to the decay rate of e to the minus k plus 1t. So the actual control effort that's going to be applied is going to look something like this. Right? This is u of t applied as the closed loop step response. Okay. The reason I'm bringing this up is because we just said up here for the closed loop step response, if we want to track a reference value of 1, oh, the key here is just to increase k. That's all we need to do, right? The larger k is, the faster we're going to converge and the better we're going to track that reference value. That's something that we established earlier. However, this is sort of your check to that phenomenon of just increasing k, right? Because if you think about it, k is just a gain, right? K is just a gain, but k also appears directly in the control effort. So if this is like an engine or something that's providing a forward thrust to a vehicle, or if this is like a motor that's providing a torque to a particular system, at some point those physical actuators are going to hit an upper limit. So in the extreme case up here of, say, we said when k was equal to 1,000, we get basically perfect tracking almost instantaneously. Well, k being 1,000 may correspond to requiring 1,000, horsepower or 1,000 newton meters at the motor drive shaft or something like that. So the problem occurs when you try and implement it, because you may not be able to actually implement this particular computed U of t. You might be limited physically by your hardware, right? Your motor might not be capable of producing what the controller is asking for, right? So that's where you're going to run into problems. And again, this just goes to illustrate the sort of balancing act that you have to play when you're doing control design, right? You want to get the best possible performance while still physically being able to implement that control scheme, right? Okay, so again, trade-off. We've got trade-offs with a larger gain controller. You're going to get a faster response. You're going to get better tracking. It's just if your K gets too large, you might not actually be able to physically implement that. Okay, so I'll just take you through one more quick example. This last example is relatively fast. It's pretty quick. So I just want to illustrate the fact that feedback control is it's a double-edged sword, right? It's super powerful. It allows you to stabilize unstable systems. It allows you to improve performance, improve tracking and robustness, and all these benefits. But you got to be careful with it, because the point that I'm going to make in this example is that, well, you can always apply feedback control, but every time you do, you run the risk of destabilizing a system that may have already been stable to begin with. Okay, so let's take a look at an example of how that works. So here's a plant, simple first order, a little bit different from last time, 2 over s plus 1. And this time our controller is not a proportional controller. It's not just a simple gain value. It's actually a transfer function as a function of s that looks like this. Okay, so remember, controllers, any C of s's that you come across, those are just transfer functions. They're input-output relationships, and so they can come in many different forms. It's not just k or just a constant value, right? It could be a transfer function like this. Now notice that this plant is stable, right? If you look at the pole of this transfer function, you got one real pole at s equals -1, so the pole is in the left half plane. Therefore, this is a stable plant. Now, when we go to implement closed loop feedback control, our closed loop transfer function from r to y is Cp over 1 plus Cp. And when I plug in this C and this P, I get basically 2s minus k over s plus 1, s plus 2, over 1 plus the same thing. Like so, right? So again, just plugging in CNP wherever I see it, and then I want to reduce all of this stuff down to a rational function, which just means one polynomial in S divided by another polynomial in S. When I do that, I get the following. And so this becomes my closed loop transfer function, right? This is how the system is actually going to behave when I close the loop. Now notice that I've taken a first order plant and I've basically turned it into a system that's going to exhibit second order dynamics. And that's typical. That happens all the time. It's because we introduced a pole in the controller. However, the thing to note is that while this is guaranteed to be stable because it's got a pole at -1, the poles of the closed loop transfer function are adjustable, right? And that's, again, kind of the whole point of feedback control is that through the use of a control parameter like k, you can actually move the closed loop poles around in the S-plane, thereby controlling the behavior of that system. Well, this is just a case of, this is almost stating the obvious, but you started with a stable system and now you've got a closed loop second order system. I need to make sure I'm only going to apply k values that preserve the stability of that system, right? It would do me no good to say, oh, here's a stable plant. I want to use feedback control to improve the performance, but then I go ahead and destabilize it. That would be bad. Okay, but we know something about stability. This is a second order closed loop transfer function, so there's no need to use the Ruth test or anything like that, because the test for the necessary and sufficient case is for all of the coefficients of the denominator polynomial to be positive, right? So if I want to guarantee closed loop stability on this second order system, what I really need is to have 2 minus 2k. I need that term to be greater than 0. And this places a constraint on k. This says that k needs to actually be less than 1. As long as k is a value smaller than 1, all the denominator coefficients will be positive, and therefore the closed loop system will be stable, and that's good. Furthermore, we typically only consider positive k values. Okay, we really only consider positive k values for any control scheme, generally speaking. At least for this, at this level, we'll consider only positive k values. So if we want to guarantee closed loop stability, we need k to stay within the range of 0 to 1. The implication here, okay, is that, well, if k is not between 0 and 1, right? I mean, the gain can be an infinite number of values, and this is a fairly small range from 0 to 1. So if k is 1.1 or 1.01 even, the system, the closed loop system, is going to be unstable. Okay, so what I'm trying to highlight here is that essentially feedback control gives us incredible power to design closed loop systems that behave to our liking, but you just have to be careful because it's very easy to destabilize a perfectly stable system if you aren't careful. Okay, so that's all I was trying to illustrate here. And the only reason we know this is because we went through and we computed our closed loop transfer function and looked at its denominator to basically sort out that k has to be within this range to guarantee closed loop stability. Okay, so this was a quicker example, but it's kind of an important one. And it highlights this fact that it's very easy to destabilize a perfectly stable system once you close the loop. Okay, so the conclusion here is well, you just got to be careful with feedback control because it is relatively easy to destabilize systems, right? So this is not a case of don't have a system close the loop and start messing around with gain values because, well, you may destabilize the system. Okay, destabilizing a system generally manifests as things physically breaking, right? You're going to exceed some actuator limitation and you're actually going to break something. Instability also could potentially draw higher current from a particular power supply than is designed for. So I'm always saying if your system goes unstable, that either means you've broken something or something is on fire, right? So it's somewhat of a joke when I say that, but there's some truth to it, right? I have done both things before. Actually, I've broken physical systems, and I've also set things on fire by having them go unstable. So all I'm saying is that feedback control is very powerful. Just be careful. Okay. In the next lectures, we're going to actually start getting into, well, how do we actually, now that we've got this framework for feedback control, how do we actually start designing controllers? Okay, how do we actually start figuring out what this C of S should look like so that we achieve the output in the closed loop sense that we want? Okay, so we're getting there little by little, and now we're, with the introduction of feedback control out of the way, now we're going to start to get in those control into those control design strategies. Okay, so we'll see you in the next one.